Okay, so let's talk about relational databases. All right, so we'll be spending half of our semester talking about relational databases in all different aspects. First, we'll talk about how to create databases and create tables and the relationships and all the different constraints, how to do queries and inserts and updates at the console. And slowly but surely, we'll be looking at different ways of interacting with it. First, we'll take a look at interacting with Java programming language. Then we'll create an abstraction around that. That's what humans do, right? We are abstract machines. We create an abstraction, we understand it, and then we put another layer, and then we put another layer, and that's that's where we go. So the first abstraction will abstract the file system. We don't want to deal with the file system. Instead we'll use SQL as an abstraction of interacting with files, right? And then we'll create another abstraction layer in that. It says, well, how do we talk about it using programming languages? And then we'll put another abstraction layer on top of that and ORMs, object relational mapping, so that we can think about the data in terms of objects as opposed to tables. And away we go. Yes, and then we'll talk about REST and so on and so forth. So, but first, let's talk about what relational databases are. So what is a database? So it's in its more generic form. A database is just a collection of pieces of data points. Yes, and any collection of data points is a database. Yeah. Ideally, we would love that for this data to have some structure, right? That these data points somehow are related to other data points, right? Or are capturing the same type of information. Maybe they have a XYZ, and they have a temperature, and they have a pressure, they have a velocity, they have whatever that is common to a whole set of other data points, right? They're all related to a particular class of data points. And you might have another set of data points that are also related to one another. And perhaps these data points are related to somehow to another set of data points. Yes. Now we refer to the abstraction layer that we talk about as these data points. We call them records. So each data point we refer to as a record, right? And each record can have any number of fields that describe that data point, right? So if it's a employee, then it might be they have a first name, last name, social security number, rates, the rate that we pay by them, right? They're hire, when they were hired, and whatnot. Yes. So here's an example of a set of data points where you have the student data point, the department, courses, sections, and enrollments, where the student is a collection of all students, right? And each one of these data points has attributes such as their first name, their last name, their GPA, perhaps what department they're enrolled in, and things like that, right? As a department, you might have the department name, what college they belong to, who the chair is, and when was the department instituted, things like that. Describe the department. The course, you might have the title of the course, who's teaching it, the department that it belongs to, how many seats are available, blah blah blah, a whole bunch of things about that course. And you have sections, enrollments. Enrollments is a special one in that most of the attributes here are for relating, creating relationships, and saying that a particular student is enrolled in a particular section, right? This is the first, one of the first clues that these data points are not just floating around on their own and collecting all the students and all the departments over here and all the courses over there, but they're actually the relationships between students and departments and sections, and students are enrolled in sections, and that relationship, the fact that we are capturing in the data point, we're capturing the fact that something is related to something else is what gives the name relational databases. The word relational, right, is captures this fact, right, that these data points, right, capture data in here that relates a data point with some other data point. This data point, the enrollment, is relating two things. It's saying that this particular student is enrolled in that particular section, and while they were enrolled in there, this is the particular grade they got. Right, that's the grade they got once they they finished that particular relationship, right? Section also is providing a relationship. Is saying that this section belongs to that particular course. Right? Also says that that course belongs to this particular department, and the student also says what department they belong to, major ID. Right? They belong to a particular department. They enroll in a particular department. Notice that the only one that doesn't have any relationship is the department. The department is all by itself. The department doesn't belong to anybody, right? Presumably, it might belong to a college, might belong to some university, perhaps, but that might be irrelevant, right? Since this is the only department in this college, or in this university, it might be irrelevant to capture the fact of what university it belongs to, right? So notice that another key important here is that the relationships usually go go from one direction to the other, right? It says that the section, for instance, points or is referring to the parent. It says, I belong to the course, right? And the course says that I belong to the department, right? And the student says that I belong to that department too. See that? Right? It's usually there's a directionality between the relationships, right? Usually we think of a kind of like a parent-child relationship, right? And using that analogy, we have that the parent is a department which has many students, right? And here's a course that has many sections, and it is a section that know about their parents, right? The section knows about the parent course. See this? That's another very important clue. It is the children who have references to their parents, right? Never the other way around. Right? It's not the parents who know about their children, which is kind of weird because if you've done object-oriented programming, usually the way you capture the data in Java or C#, usually is the parent who has references to the children. See that? Right? It is the parent who has an array of children. Right? That's one of the big problems later on we're going to find later on when we talk about ORMs, object and relational mapping. There's these two worlds, right? They're not very compatible with one another, right? The relational world, you have the children referencing to the parents, but you have the object world, which is backwards. It is the parents who have references to the children. So that's one of the big challenges that we're going to find later on how to map these two different worlds, and usually we refer to it as the impedance problems. There's an impedance between these two worlds, right? So anyway, we'll get to that. Another thing that we're pointing out here is that this enrollment, right, has references to two places. It says, hey, that student over there is referencing is related to this particular section over there, right? So we usually refer to that as a many-to-many relationship, right? Many students are enrolled in many sections, right? And many sections have many students enrolled in it. Right, it's a many-to-many between those, right? We refer to this sometimes as a mapping table, right? And depending on whether this data point has only references, or it has references, but it also has real data. Notice that the only real data here is grade, right? Everything else is just relationships, right? So if we say that this particular data point, if it only has relationships, right, typically we call this a mapping table. It's mapping those things, maps them to those other things, right? These students are related somehow to these sections. We call that just a mapping table, right? But if it has at least one other field that is not relationship, that it actually has real data, right? We call this an association. It's a nomenclature, it's a jargon. If it has data, we call it an association. If it doesn't have data and it's only relationship, we just call it a mapping table. Yes, it will be in the quiz. Also, other things here, right? Notice that a lot of these fields have IDs in them, right? Section ID and course ID and so on and so forth. So a lot of them just have a lot of these IDs, and they are used for uniquely identifying each data point, right? Each data point needs to be uniquely identified, right? And we use them. The way typically we do that is through unique identifiers, right? For instance, the student has an SID, the department has a DID, the course has a CID, and so on and so forth, right? These uniquely identify these data points, and they are used for other data points to be able to refer to those unique identifiers. See that? Right? So here's the section ID and student ID are referring to that section ID, right? And that student ID over there, right? So we usually refer to these as keys, right? These anything that ends with an ID here, typically we refer to them as keys. Um, the ones that are used for uniquely identifying a data point, we call them primary keys, right? That are unique within its own data set, right? And then you have all these other keys are referring to those primary keys, right? And we refer to them as foreign keys, right? They're referring to something that is outside of the data set, right? It's foreign. So these are primary keys, and these are foreign keys, right? We'll come back to that, all this nomenclature as we progress. So the collection of all these data sets, the collection of deciding that I broke out my data set into students and sections and whatnot. We call the collection of all these tables and classes and whatnot, we call it a schema, right? The set of all the data definitions and what attributes and the data types, we call it the schema. And we're going to be using this schema all throughout at least the first half of the semester. We're going to be using this fictional schema of a university. It's a very small university. It has 3 departments. It has 9 students. It's a very small university. And we'll come back to this schema all throughout the first half of the semester. So students, departments, course, sections, and enrollments. It's a university database. It has students, enrollments. We say that a record, right, a particular record, we refer to as an instance, right? We say that this is a particular instance of a section, right, that says that this section number 33, belongs to course 32, and Professor Newton is teaching it and was offered in the year 2000. Okay, same thing like the students over there, right? Every record is referred to as an instance of a student, right? A real instance. Ideally, all these records presumably are representing some physical phenomenon, right, in real life, yeah, that you can query and respond. Notice a curious choice here for the professor, right? Notice that typically, knowing the domain, you would typically decide to capture the professor. You might think that the professor is important enough that it would have its own class, right? Where you might have a list of professors, right? Where each one has a first name, last name, has maybe the office that their particular office, their office hours is there and whatnot, right? Call what college they belong to, when they were hired, tenured, and all sorts of information about the professor. Yes, but here, we make the curious decision that the professor, we only have the username of the professor. We don't have anything else about the professor, right? It's the only field that we have, right? So the decision was that the only real place where we are capturing the professor information is right here. It's just a field as opposed to an entire class. And those are kind of decisions that you will have to make yourself, right? Whether something is important enough that I want to capture, has its own class with all sorts of fields, right? Or is not as relevant, and it's just an attribute in somewhere else. Yes, deciding these things, whether something is a class or deciding whether it's an attribute, what data types you're going to use. We call that designing the database, right? And that the process of making those decisions is the design process. Okay. Right. So a couple of characteristics of databases: they are persistent, meaning even if you have power failure, the data will still be there tomorrow, right? If you shut it down, you come back tomorrow, it's still there. So it's in permanent storage. It can deal with large amounts of data, usually several orders of magnitude more than what you could possibly load at any one time in memory, right? So whenever you are interacting with a piece of data, with a database through a piece of software, usually you will only be looking at a small snippet of the entire data set, right? Because typically, maybe you have a machine and you would maybe load a gigabyte of memory maybe and take a look at that. Yeah, but usually the database might be several terabytes big, right? So usually you will only be looking at a small cached version of the actual data in the database, right? So, but databases are meant to be able to deal with large amounts of data, right? Shared, meaning usually it won't be only you who is accessing the database, right? It'll be hundreds of people, thousands, millions of people accessing the same database, right? How do you deal with that, right? What if I'm updating something that somebody else is reading, right? Maybe somebody's depositing data into my son's account, and while they're withdrawing, right? Will there be a problem whether I deposit before you withdraw, right? It'll be a concurrency issue there, right? So we have to deal with those kinds of things, right? It must be accurate, right? That ideally the data, as it evolves, as the state of your data evolves by somebody updating and inserting and deleting and whatnot, right? It's always in a consistent state. Usable meaning some user interface that can be that allows you to access the information, and usually there's a DBA administrator that knows how to maintain the health of the database. Record storage. So again, there is a file. Usually all this data actually eventually will make it into some kind of file system. The structure and the of how is it stored. Usually it's vendor specific, right? Each vendor will have its own way of encrypting or storing this data into a file system. We're not going to be dealing with those kinds of issues. The only thing that perhaps might be interesting is that usually there will be several files, for any data set or any data point. It might be stored across multiple files, right? For instance, when you have a phone book, right? If you have a phone book, a database that has all the phone numbers, usually, depending on how big your phone book is, it might be stored across multiple files. Yes, and it's a responsibility of the database to make it look as if it were just one thing, right? It's irrelevant to you as a user whether how it splits it into multiple files. But you might also have different versions of the same database, right? Depending on how you want to retrieve that data, right? Usually, if it's a phone book, you want to look it up by maybe a last name, yes? And usually that your phone database will be indexed by the last name because that's the most common way of searching, right? If it's organized and sorted by last name, you could use you can do a binary search right through it and finding it. But if it's not, imagine a phone book that is not sorted by last name, right? Then it would take you a long time to find anything, right? You have to go one by one, right? But what if you want to search it by some other way? You want to search it by, you don't have the last name, you have the phone, right? You kind of want to do a reverse lookup, right? You have the phone number, you don't have the last name. Now, even though it's indexed by last name, it's useless to you, right? You're still going to have to look it up one by one, right? But if it's a very common way of searching it, well, wouldn't it be nice if you had a different version of the same database, but indexed on the phone? Yes. So having multiple versions of the same database is very common, based on how is it that you're going to, what are the most common ways that you're going to search through your data? What kind of select statements you're going to have and query? So usually you will have multiple index files, auxiliary files that allows to search the same data set, but through different keys, right? Through different values, different fields. Make sense? So you might have multiple versions of the same data, which are represented in many other files, index files. Multi-user access. So again, many people trying to access the same data. How is it that we can handle it in such a way that we're not stepping on each other's toes, rather you're not overriding something that I'm looking at, and we want to eliminate the risk of inconsistency. For instance, if you're looking at a travel place, right, or Expedia or whatever, and you're trying to book a flight, and it says that you have 40 seats available, you go in and book a seat, but maybe you're taking too long, right? But you're not the only one looking at the seats, right? There's a whole 100,000 other folks that want to go to Spain over the holidays, right? And they're all trying to, how is it that you could reconcile the fact that I booked this, but you too booked it, right? Is there a sequence? Do you lock the information while some timer goes on? So how do you deal with this concurrency, right? And having some possible inconsistency. You have to be able to determine how is it you're going to block others before allowing others to go, right? And so there's many strategies to handle this. The fastest way, or the most ideal would be that you assume there's not going to be any inconsistency, right? That's a very optimistic. It could be a very optimistic concurrency strategy. There won't be any inconsistency, right? And then just you don't do anything, right? That's one lazy way of solving it. The other extreme is that I'll lock everything, right? If you're looking at the data, I'm just going to lock out anyone else. Only you are looking at this, right? And only you are updating it. That means you have another 100,000 people waiting for you to finish, right? So that's between those two extremes. There's a whole bunch of other gray areas of how to do it, right? Usually you don't want chaos, anything goes, but you don't either want the other extreme where only you are looking at this and you have all these other folks waiting for you, right? So there's different strategies. We'll take a look at how is it that we can do some compromise between the two, and typically we'll be using mechanisms called as transactions that allow you to demarcate when a particular update of database is happening, right? And allows us to identify whether there'll be an inconsistency. If there is an inconsistency, how do we resolve that inconsistency? And transactions allow us to do that. Also, authentication authorization. Databases need to allow you to maintain some form of knowing who you are, right? But you identify and whether you can have authority to access certain things, right? So first I need to know to identify you, who you are. And once I've identified you, I need to, so first is authentication. I need to know who you are. And once I know who you are, I need to authorize you. What can you do once I know who you are? Right. So, well, you can touch these tables, but not these other tables, right? You can do over here. You can only do a read, right? But you can't do any writes, right? And I should be able to establish what kind of authorizations and what privileges are for your particular role. Also, memory management, right? There's again in the files, and the file system is going to have many terabytes amounts of data, but the computer can only hold a small snippet of it, right? And meaning that you're only ever going to look at you're always going to be working with a stale version of whatever the real data is in the file system, right? Because once you read it and you copy it into RAM, you are already stale. You're not working with the actual data. So there's always a risk of that someone else touching the real data while you're working with stale data, right? So how do you deal with those kinds of things, right? Although software wants to avoid having to go to the file system so many times, right? Because the file system typically is many orders of magnitude slower, right, than whatever I copy into RAM, any operations that I could make in RAM, right? So I want to minimize the I/O time, right, but also mitigate the risk that the more I cache into memory, the more risky it is that I'm working with stale data. So how do you deal with those kinds of things? So databases deal with those things, right? And also being able to automate the synchronization of whatever's in RAM and whatever's stored in the database, and survive system crashes. That the system crashes might put the database into an inconsistent state. So there's also the fact that we're going to design the file system, the data model, right? What we mean by data model, what we mean by modeling, in general, is creating a formal representation, right, of some phenomena, right? We want to create an abstraction representation of some real phenomenon, right? Now, other industries, the way they represent real phenomena, right, in the life sciences or in other engineering fields, they represent real phenomena by using equations, right? This equation explains to me how the relationship between current and voltage and resistance, or the magnetic field and whatnot, and so they have all these equations that allow them to represent real phenomena, but in an abstraction, right? That allows me to plug in some data and find how something will behave, right? And maybe answer some questions and simulations, right? On how something is going to behave in real life, but in a safe environment where I can do pen and paper. The things that we model is information. That's our business. We're in the information business. right? So we need to model data that presumably represents real phenomena, right? And we need to be able to decide what pieces of information are relevant or not, right? And what kind of accuracy do we care, right? If it's a if it's a game, then maybe gravity is very important. Well, it depends what type of game, right? If it's a if it's a shooter game, or if it's a jumping game, whatnot, right? Maybe gravity is very important, right? So I want to model gravity to very specific. But if it's a MATLAB or something where I want to do some computation, maybe it's just a value, right? I don't need to I don't need to render it. I don't need to do real time computations, right? I can do so depending on where you are. What is it that you're modeling? The type of information depends, right? If you're a Ford Motor Company, a car is very important, right? So you want to know everything, the windshield and every down to every single bolt that goes into that vehicle. Yes, but if you're in the university, a vehicle might be just a license plate. That's all you really need, right? You don't need all the bolts and all the details. So depending on your domain, on where you are, the same concept might be very, very detailed, or it might be just a field in some other attribute in some yes. So the way of the level of modeling depends also in the domain that you're in. Yes, how you represent the information that you care. It depends what kind of questions you want to be able to answer. Right? Ford Motor Company might really care about all, answering how many bolts did I use per hour, right? Whereas we don't care about those things in a university setting. It might be caring about whether you have a parking permit or not to park in our parking lots. Yes. So it depends what kind of question. Um, so data modeling is those decisions that you make to determine what kind of information you're capturing and what is the relationship, and creating a schema that represents those decisions. Now there's the file system data model on how I'm going to capture all this in a file system and how I'm going to structure it. Typically, we're not going to be caring about those kinds of things. The vendor cares a lot about how data is going to be spread over multiple files and the encryption and whatnot, how many blocks of data in the file system I'm going to use to store certain records. We're going to be caring more on a conceptual model, right? The relational data model is a conceptual model, right? And we're going to be thinking instead of in terms of tables, records, and the relationships between those records. So again, the file system is an example of a physical model, right? That I am storing it in a binary file or a CSV file, right? Or in a text file. Whereas we care mostly on a relational model. Now, the relational model came from kind of getting tired of writing stuff like this, right? Whenever if you have data stored in a CSV file or whatever binary format you care, typically if you want to query it and answer certain questions, typically you would write a piece of code that would read the file, do the calculations and the string manipulation and the calculations, and it would respond. It says, well, give me all the students from 1997. Okay, fine. Let me read the comma separated value. As I read each one, I split the lines of that I read, and you retrieve the second element in the second column. If it's 1997, I kind of capture it, and I respond to you. Oh, these are the results of all the students in 1997. So we never want to do that ever again, right? Instead, we create this abstraction that there are tables of students, and instead we like to be able to do some things like this. There's a table called students that we want to select all the names of all the students where the graduation year is equal to 1997, right? Obviously, this would have to be converted somehow behind the scenes into a loop, right? That loops through all the records and does the comparisons of each field looking for 1997. Yes, right? So compiling this high level query into that other lower level query, right, is what databases does for us, right? The abstraction layer. Okay. So presumably there's a student table, which represents all the records, has these four fields, student name, the graduation year, and whatnot. And this query allows us to think about the query in a very, very high level, using this SQL query language. There are certainly many other data models. There's graph-based data models, object-oriented data models, hierarchical data models. later on when we talk about non-relational databases, Mongo, we'll be talking about an object database, right? In Mongo, and it allows us to store and retrieve objects, as opposed to storing records, right, and fields. It allows us to take a JSON object, and verbatim store it, right, into a file, right, into a database, and then be able to retrieve that object, from the database and reinstantiate that into RAM, right? So that will be an example of an object database that will be playing around a little later, right? Also, JPA is another form, right, that allows us to think about the records in terms of objects as well. RMI allows us to store objects into the file system as well. Hierarchical data models, things like XML, right, or Firebase, or these systems that allow you to recursively store data instead of other parent data, allows you to create hierarchical graphs that like XML, and we'll talk about that a little later as we go. There's also real-time databases, right? Real-time databases where the data is not static. Right? You're measuring the temperature or the pressure or the speed or whatever, right? It's data that is changing all the time. Right, so it's not a record that stays there fixed in time, right? It's changing over time, right? So even though the data is changing, you still want to be doing queries. What's the average? What's the tendency? Is it growing? Is it slowing down? Is it, right? You want to look, and your queries will depend typically on a window of time. Is it within the last hour, within the last week, within the last month? What has the data going up and down and whatnot, right? So there are also real-time databases that allow you to query data that is changing all the time. So we won't take a look at that. Maybe, yeah. I think the last week we'll talk about real-time databases. A physical database dependency. The database is responsible for allowing you to go between all these representations of the data, between the file system into a conceptual model, and then representing it for you for consumption for the human. Where is it? There's and for the human, it might be that the human, different types of humans, or different audience, right? Different audience might want to query the data in a different way, right? Me as a faculty, I might be interested in just my courses, right? But if I'm a registrar's office, I might be interested across many courses, right? And so I might have the authorization only to look about data that is where I'm a faculty, right? But I might log in, as a faculty. I might also be part of some committee, right? That might give me authorization to look across multiple courses. Yes, and so depending on the audience, even if it's the same data set, I might be interested in different queries. So databases allow you to, most vendors allow you to create a conceptual model, data model, but also an external schema. Schemas, virtual schemas, meaning schemas that, excuse me, the data can be represented in and stored in a particular way, right? But we might create a virtual representation of that data depending on who the audience is, right? We'll see a little later that the way we decide to store it for permanent storage usually is a normalized representation, right? We would break out the different tables and the different to eliminate redundancy. Yeah, but for somebody who's querying it, typically the query will involve joining data that belongs to one data set, joining it with data with some other data set, right? And depending who the audience is, this might be very inconvenient, right? Because I don't know how to join, right? I don't know any of that SQL stuff, right? Why don't you just give me everything in a single table that has everything? But usually we have gone through a lot of effort at splitting it into multiple tables to avoid redundancy and inconsistency, right? But the audience might want it as a convenience, right, to have it all in a single spreadsheet. Why don't you just give me one spreadsheet that has all the columns with everything, right? Usually that creates data that is very, very redundant. That has the information of the professor repeated many, many times, and the sections repeated many, many, many times, right? And we already went through the process of breaking it out. But depending on the audience, they might find it inconvenient, and they might prefer to have it in a single place. So external schemas allows us to do that. So the schemas allow us to create virtual schemas, right? That allow us for the convenience of different audience. So we might have gone through the process of splitting the tables into student tables and enrollment tables and sections and courses and departments. It's nicely normalized. There's no redundancy, but from the dean's office, right, or the faculty or the registrar's office, it's very inconvenient to have to, if I need grades and I want to know who's in the dean's list, this semester, it's very inconvenient to do all these joins from here to there and all the data. So I might provide a virtual set of tables, the student info and the student course that joins the data into a very convenient way of consuming the data, right? And usually that's a denormalization, and we'll talk about those kinds of things. And you do that with views, right, or materialized views. We'll talk about that a little later.